Okay, here's a simple example of using the Laplace transform method to solve a differential equation. So the diffie we're going to pick is y double prime minus y equals t. So you can see this is a non-homogeneous second order linear equation. It also has some boundary conditions. Y naught is equal to 1 and y prime naught is equal to 1. Okay, the first thing I want to do is find the Laplace transform of the input function. So remember, that's equal to r, which is the Laplace transform in this case of t, and looking on the table, that's 1 over s squared. I'm going to need that for the substitution because we're going to substitute this into what is the solution to the algebraic equation. And the algebraic equation ys is going to be equal to s minus a times the quantity y naught plus y prime naught plus r. And all that is times q, which is s squared plus sa plus b. Well, now we can substitute all this stuff in. Because we know that r is the Laplace transform of t, that's 1 over s squared. We know that y naught and y prime naught are both 1. And of course, a is equal to 0 in this case. The leading coefficient's 1, the a coefficient 0, and the b coefficient is negative 1. You'll notice, though, that the b coefficient only appears once, and that's right down here at the end. So when I do all that substitution, I'll get s plus 1 plus 1 over s squared, and then all of that over what the denominator turns out to be, and that's s squared minus 1. Now, unfortunately, if I were to look on the table right now of Laplace transforms, this is unrecognizably complex. So I'm not going to be able to immediately transform it. What I'm going to have to do is break this into a series of fractions. So the first step is pretty easy. If I just put s plus 1 over s squared minus 1, then that guy right there, well, let's write the second part too, plus 1 over s squared minus 1. So this is what it would turn into if I broke it into two fractions. This first one then is just 1 over s minus 1. So I can sort of write that off to the side. So this is 1 over s minus 1 because this guy factors as a difference of squares and the positive conjugate cancels, all right? The problem is I have to devolve this one. There's nothing that contains anything like this. Products in the denominator, they're usually sums or differences. So I'm probably going to have to decompose this into multiple fractions. So let's look at what that looks like. So it's 1 over s squared times s squared minus 1. In actuality, the s squared minus 1 is okay. I can leave that as one of my partial fractions, but I'm going to have to break the other one down. So what I want to do is break it into three potential fractions, a over s plus b over s squared plus c over s squared minus 1. Now, normally when I would do partial fraction decomposition, I would actually have a c and a d term because I would have s plus 1 and s minus 1 under c and d. But in this case, the s squared minus 1 as a denominator is just fine. There are several forms of Laplace transforms that have s squared plus or minus a squared, and so I'll be okay with this, all right? Okay, well, remember, the process for partial fraction decomposition is to first select your partial fractions that you're decomposing into, and then you want to form a series of equations to find what these coefficients need to be in order for this sum to be identically equal to this rational expression. And to do that, we simply make the denominators common, and we write down what the new numerators are going to be. So A is going to need an s and an s squared minus 1. So as and s squared minus 1. B is just going to need an s squared minus 1. And finally, C is just going to need an s squared. And I know that the sum of all of this equals the numerator of the rational expression I'm trying to match. So it all equals 1. Well, now we do just what we usually do with a system of equations with differential equations. We match the coefficients of the like terms. So I'm going to have as cubed minus as plus bs squared minus b plus cs squared, and all that equals 1. Well, you can see there's no s squared term, so that means a plus b plus c has to be 0. A plus b plus c has to be 0 because there's no s squared term over here. So that takes care of these. As is the only s term, so negative as also has to be equal to 0. Whoops, just negative a, because there's no s term. And finally, negative b, which is the only constant term, has to be equal to 1. So I know now that b is equal to negative 1. I know that a is equal to 0. So I just need to figure out what c is. So 0 minus 1 plus c equals 0. That means c is equal to 1. So I can take these back up here and say, okay, c is 1. B is negative 1, so 1, and make this negative, and a is equal to 0. So this term goes away entirely. So this right here is the same as that. They are identical. And that means over here it's the same also. So now I can just write this in. So this is plus 1 over s squared minus 1 minus 1 over s squared. So if all of this represents the Laplace transform of my solution, then each one of these has an inverse transform which will produce my solution, y of t. So I look on the table and 1 over s minus 1, that's equal to e to the t. 1 over s squared minus 1, that is the hyperbolic sine of t. And 1 over s squared, as we started with, is just t itself, so minus t. And this actually is the solution to this second order differential equation. And as you saw, using the method of Laplace is an easy way of turning the differential equation into an algebraic equation and then working algebraically with it until we can turn it using the inverse Laplace transform back into the functions that actually represent the solution. All right? Okay, so that's your example problem. You could do all the homework problems from this alone, but I do want to do one more sample problem for you. What that's going to do is allow you to shift these from non-zero positions. What happens if the initial conditions are not at 0? Well, unfortunately, we can't use the Laplace transform method unless they are at 0. So we're going to look at a way to transfer these initial conditions from wherever they are to 0.